Okay, so good morning, good afternoon, everyone. And thanks a lot for the opportunity to give you this talk today. I'm very sorry that I cannot be there in person, and I hope there will be another occasion very soon. So today I would like to talk about one of my favorite scientific topics, that is tidal disruption events. And in particular, I would like to talk, I would like to convince you, I hope, of why I think these sources can be very interesting for future decihertz observatories. Okay, so let me start from the beginning. What is a tidal disruption events? Well, these events occur when a star orbiting around a massive black hole gets disrupted by the tides induced by the black hole. And when the star is passing through the pericenter, the tides basically turn apart the entire star. After the disruption, we expect roughly half of the stellar debris to circularize around the black hole, and eventually they could form an accretion disk. So during the circularization phase, actually the stellar debris starts to accrete onto the central black hole, and there is production of very luminous electromagnetic flares. And thanks to this electromagnetic emission, to date, we have been able to observe already 100 tidal disruption events, at least 100 robust tidal disruption events, mainly in X-ray and optical. Furthermore, in the coming years, we expect actually to be able to detect, in the most optimistic scenario, 1,000 tidal disruption events in electromagnetic per year, thanks to new telescopes that will be operative, like the Roman telescope and the Vera Rubin Observatory. So the reason why actually I find tidal disruption events so interesting is because they are multi-messenger emitters. So as I told you, they first of all emit electromagnetic radiation, and actually so far we basically only have electromagnetic observation tidal disruption events, which allow us to study, to observe directly what happens after the disruption. We're talking about like delay of hours to days after the disruption, depending on the black hole mass, the characteristic of the star. Yet, we also expect a tidal disruption event to emit high-energy neutrinos from the later stages, when there is also possible production of jets. And actually, there are already a few potential candidates of astrophysical neutrinos from TDEs. Furthermore, we also expect them to emit gravitational waves. And in particular, today we talk about the monochromatic gravitational wave burst that is produced when the star is disrupted at the pericenter. So let's start with some order of magnitudes to understand a little bit of what we are talking actually. So we can estimate the peak of the gravitational wave strain and the associated frequency from tidal disruption, or gravitational waves from tidal disruption events through these two formulas, where you can see that we have the following parameters. So the mass of the star and the radius of the star, the mass of the black hole, the distance of the source, and the beta parameter. So actually the beta parameter is something really typical of tidal disruption events and is a dimensionless quantity that tells us how much close the star is to the black hole. In particular, is defined as the ratio between the tidal radius, that is the maximum distance that a star can have from a black hole and still be tidally disrupted, and the stellar pericenter. Then I will talk a little bit more about the penetration factor later in the talk. So, if actually we consider what is called the standard TD scenario, that is a sun-like star disrupted by a million solar mass black hole at a distance of 20 megaparsec, well, we expect an average strain around 10 to minus 22 with frequency around 10 to minus 4 hertz. But then both the strain and the frequency actually can increase thanks to the penetration factor that I was showing you before. As for the typical case of a white dwarf disrupted instead by an intermediate mass black hole, well, we expect a strain similar, always around 10 to minus 22, but a higher frequency around the decihertz. So these very simple analytical estimates basically show that the tidal disruption events emit gravitational waves in the frequency window where the future space-based detector will work. First of all, LISA, that we already know it will be launched in 2030s, but then also all the possible family of the decihertz observatory, like the Lunar Gravitational-wave antenna, but also, for instance, the SIRCO. So, for sure, in the upcoming years, we will see for the first time tidal disruption event through gravitational waves, and we also have for the first time multi-messenger observation of these events. Yet it is very important that we understand actually now how this signal look like, which are the main features, which kind of information we can extract from it before these instruments will be operative. So in order actually to understand what is the gravitational wave signal from an individual tidal disruption events, we need to do a numerical work. When we want to simulate astrophysical system, we do hydrodynamical simulation. And in particular, if we are interested in simulating tidal disruption events, since they are non-axis symmetric system, normally it is more practical to use a code based on a Lagrangian description of hydrodynamics. In particular, I use a code, Phantom, that is a smoothed particle hydrodynamics code, open source, that allows to do a simulation in 3D of astrophysical system, and in particular allows to do simulation in a fixed background metric, like the Kerr metric. So, within this code, I implemented an algorithm for the derivation of the gravitational wave emission. In particular, this algorithm is based on the quadruple approximation. So basically, we are considering the gravitational wave emission proportional to the second time derivative of the moment of inertia of the system. And then we also consider an angular distribution because we have to, for instance, consider different angles with which we are observing the system, for sure. So once I actually implemented this tool, after testing that everything was working properly, I start to use this module to derive the gravitational wave emission from tidal disruption events. And here, for instance, you can see the gravitational waves from a standard TDE, a sun-like star disrupted by 1 million solar masses and Beckel at 20 megaparsec, and we are looking the system face on. Yet, in order to really understand actually all the properties of this gravitational wave signal, we need to investigate a very wide parameter space, because actually this signal depends on many parameters: the black hole mass, the stellar mass, the penetration factor, the black hole spin, and others. So I started to do this investigation. For the moment, I already collected 200 waveforms from tidal disruption events that are in this online catalog. If someone is interested, feel free to use them to do your study. And already from this initial investigation of the parameter space, we found something very interesting, for instance. For instance, we actually found that the gravitational wave signal from a TDE, as is reasonable to think, is affected by the black hole spin, and in particular, decreases for higher values of the black hole spin if the orbit is prograde. The opposite trend is verified is if the orbit is retrograde. We also actually found, as we expected, that if the black hole is not rotating, since there is spherical symmetry, the gravitational wave signal is not affected by different inclination angle of the stellar orbit. But this is not true in general if the black hole is rotating and the star is getting closer and closer to the black hole. So just let me say that this investigation of the main features of the waveforms and tidal disruption events is still at the beginning. As a matter of fact, there are still a lot of waveforms to produce for different combination of the parameters, But still, I think like creating such a catalog can be very useful, because then it can be used, for instance, by the community to do multi-messenger study of tidal disruption events. And for instance, to see if multi-messenger observation of TDs can be used to constrain cosmological parameters like the Hubble constant. Yet, it's not only important to understand which are the features of this signal and how different parameters can change it, but we also need to understand what are possible detection rate. So, unfortunately, if we consider LISA, it's very unlikely that this instrument will be able to see the gravitational wave emission from individual tidal disruption events. So for this reason, we thought that it could be interesting to actually study the gravitational wave signal produced not by an individual TD, but by the entire population of tidal disruption events for the universe. That is the gravitational wave background from these sources. And in order to do this, actually, we divided the tidal disruption events in two classes, let me say. What we call the nuclear tidal disruption events, where we are considering a main sequence stars disrupted by a supermassive black hole in the core of a galaxy, and what we call the globular tidal disruption events, where we were considering white dwarfs tidally disrupted by intermediate mass black hole in globular cluster. That is black hole with masses in the ranges between 1,000 solar masses and maximum 10 to 5 solar masses. So this is actually a population of black hole different from the one we were considering before. And what we found? Well, we found that as a consequence of the impulsive nature of the gravitational wave burst from TDs, actually this background was proportional to the frequency to -1/2. And as you actually can see in this plot, this was like the most optimistic scenario of our study, the background from main sequence stars disrupted by supermassive black holes seems to be in a part of the frequency window where there are no future detectors, at least for the moment, sensitive enough to see it, even if now there is like a follow-up study that tries to change some hypotheses and see if the situation can improve. Yet, from our study, it was very clear, actually, that the background from globular tidal disruption events instead was a promising source for decihertz observatory. And in particular, its possible detection could give us insight about the distribution of globular clusters, but also the occupation fraction of intermediate mass black hole in these environments. Another very interesting thing that we can actually study when we want to understand a little bit more the gravitational waves from tidal disruption events is gravitational lensing applied to this signal. So we talk about gravitational lensing when there is a massive object, the lens, between the source and the observer, and this massive object is bending the surrounding space-time, thus causing a deviation from the signal that we want to study from its original path. Actually, gravitational lensing can have some very interesting consequences. For instance, it can produce multiple images of the source, and it can also magnify the signal. And in general, for the future detection that we will have of tidal disruption events, it's very important to understand if between the observed events there are lensed events, in order to avoid errors in the reconstruction of the parameters that describe the source, like the distance of the source. So actually what we did was to perform this study where we took two reference interferometers, LISA for the millihertz regime, more sensitive in the millihertz, and the SIGO more sensitive in the decihertz. And we build our population of lenses that we were considering galaxies with an hybrid model, where basically for low redshift, that is redshift smaller than 1, we were basically using a semi-analytic approach where the galaxies were modeled like singular exothermal sphere, while at higher redshift, Z bigger than 1, we were using the results from ray tracing simulation. And what we found was that actually the SIGO, so our prototype of decihertz interferometer, should observe strongly lensed tidal disruption events, in particular around 130, and the majority of these lensed events will be at redshift higher than 1. Okay, so in general, we expect that from the future, with LISA, probably we will not be able to see gravitational waves from single tidal disruption events, but with the CHERS observatory, the situation will be very different. In particular, we expect that the SIGO and BBO can potentially observe 1,000 tidal disruption events in gravitational waves per year. But what about possible detection of tidal disruption events from the moon, like for instance through the lunar gravitational wave antenna? Well, in these two plots, I show the case of a TD of a sun-like star disrupted by an intermediate mass black hole, and the mass of the black hole is plotted on the x-axis, while on the right side, I consider the TD of a white dwarf. And I show what is the maximum distance at which the lunar gravitational wave antenna can actually observe these tidal disruption events in gravitational waves. So you can see that in general, we can go beyond our galaxy, and actually we can start to see these events also in galaxies close to us, like the Large Magellanic Cloud, for instance. Still, it's something promising, but it's true. It's very close to us. There is actually a way maybe to improve this horizon of detection for LGWA, where actually, yes, there is a possibility. Because so far, I was actually describing the scenario when the star orbiting around the black hole is fully disrupted by the black hole tides. Yet, there is also the possibility that actually the star is only partially disrupted. So if we go back to the penetration factor, the beta parameter, normally we say, okay, for beta bigger than 1, we have the full disruption. For beta smaller than 1, we don't have any disruption. But there is like a range of parameters around 1 where actually only the external layers of the star are stripped away, and then the rest of the star survives and undergoes many passages around the black hole, many pericenter passages. It's not very easy actually to understand exactly what is this range of the beta parameters where we have the partial TD scenario, because it really depends also on the internal structure of the star, but still there is this possibility. And it's not only something theoretical. We already have some observation, electromagnetic observation, what we call the quasi-periodic eruption, that could be actually explained with a model of a partial tidal disruption. So why partial TDs can be actually potentially more interesting than full tidal disruption events? Well, because as a recent study actually show, even if they were talking about higher black hole masses with respect to the range I'm interested in, yet they show that we expect the rate of partial TDs to be actually higher than the rate of full tidal disruption events. So this is something, first of all, very important to consider. And then we also have to consider that actually the star can survive around the black hole in these repeating passages for many orbits. And so since we have actually a higher number of cycles, we can have an increase in the signal-to-noise ratio of the gravitational wave signal emitted by this source. So for instance, as I show you in this plot, which is very preliminary, so please take this result with caution, because then maybe more detailed the calculation can change it. But in any case, from these first estimates, here I consider again the white dwarf disrupted by the same range of black hole masses as in the previous slide. But in this case, I'm assuming that actually the white dwarf is undergoing a partial disruption. So it continues to orbit around the black hole, in particular in this case for 700 orbits. And as you can see, actually, the horizon at which LGWA can actually detect the signal from this system has increased. In particular, now, if we consider like a very optimistic and understand the threshold for detection of 5, we can actually reach the Virgo cluster. So let me conclude my presentation says that for sure in the next years we will be able to see tidal disruption events through multi-messenger, through different messenger electromagnetics, which is something that we already are able to do, and in the future also gravitational waves. And actually to detect tidal disruption events, decihertz interferometer are much more promising than LISA or other possible detectors more sensitive in the milliards. In particular, if we focus on tidal disruption events involving intermediate mass black hole, actually a detection of these events can provide us information on the intermediate mass black hole distribution for the universe, which will be like one of the first time actually we could be able to reconstruct this information. Probably partial tidal disruption events are sources more promising to observe in gravitational waves. Still, they can be problematic because we need to understand actually how many of these events we can expect realistically. And this is something that is not very easy to calculate, and we need to think about it. So I thank you for your attention, and if you have any question, please, I'm here.
Thank you, Martina. Are there any questions?
I'm missing something. How can we recognize that a TDA gravitational wave is lensed, distinguished from non-lensed?
Yeah, I mean, you mean from a data analysis technique point of view?
Yes.
Okay, so that is something that we, okay. So actually the goal of our work was try to understand, first of all, if we can, if lens tidal disruption events will actually be observed by future detectors, and the answer was yes. But from a data analysis point of view, we still have to understand actually which is the best technique to use to understand how to recognize a lensed DE from a non-lensed one. So it's still something that we have to figure out, yes.
So I have a question. If you had to make a guess today, what horizon you would like to have for these events, or or what would be your guess to have a few detections? I mean, you say there are question marks, like how many of these partial TDEs?
Yeah.
But do you have a guess if is Virgo going to be enough, or you need to go beyond that?
No, I think actually the Virgo cluster actually can be already enough, because at some point, sorry. Okay, so at some point here I was actually just cited very briefly. I mean, I wrote it a paper where actually we try to explain a quasi-periodic eruption that we observed as a possible partial TDE of a white dwarf around a 700 solar mass black hole. And actually, this source that we try to explain in this way is in the Virgo cluster.
Okay, that's interesting. Okay.
Then it also depends when which will be a realistic signal-to-noise ratio threshold for detection. Because as you can see from this plot, for instance, the Virgo cluster is reached, but at least in this, considering this black hole mass range, with a signal-to-noise ratio threshold of 5, that I understand is a bit low.
Yeah, might be. On the other hand, we have like eight signal channels. So if it consistently appears in all of them, then maybe there's something to it. But okay. Other questions? Okay, if not, let's thank Martina again.
Thanks to you.